Hello, my name is Valentin Peretroukhin, and on behalf of my collaborators at the University of Toronto and MIT, I'd like to present our work entitled A Smooth Representation of Belief over SO3 for Deep Rotation Learning with Uncertainty. That is a mouthful, so I'd like to unpack what an SO3 representation is, what it means for it to be smooth, what makes a representation a belief, and why these properties matter for learning. Let's begin with SO3. Estimating the rotation of a rigid body is a fundamental part of many applications in robotics and aerospace engineering. Rotations in three dimensions can be formalized by the special orthogonal Lie group SO3, whose elements are 3x3 matrices. In addition to such matrices, other ways to encode elements of SO3 include Euler angles and unit quaternions. The latter are a popular option in learning for their algebraic and geometric simplicity. However, Giamou et al. Recently identified an important shortcoming of unit quaternions in the context of learned models and introduced their own 6D representation. Building off of their insights, we introduce our own novel representation of SO3 based on 4x4 symmetric matrices. As a motivating example, we take the Wahba problem, which originates from the context of satellite attitude determination and seeks a least squares estimate of the rotation that best aligns two sets of noisy point measurements. This problem can be elegantly formulated as a quadratically constrained quadratic program over unit quaternions, where the data matrix A summarizes correspondences and uncertainty. We motivate our representation by generalizing the Wahba problem to a parametric form, where we use the solution of a QCQP to map a symmetric matrix to a unique SO3 element. Such a parametric QCQP admits a closed-form solution via an eigendecomposition and an analytic gradient via application of the implicit function theorem. Many deep learning libraries such as PyTorch already include a differentiable eigendecomposition implemented in this manner. A standard network trained to solve 3D perception tasks might simply normalize a 4-vector and interpret the output as unit quaternion. In comparison, our approach requires the network to output a 10-vector, which we interpret as parametrizing an optimization problem. Now, what does it mean for our representation to be smooth? In the recent paper, Giamou et al. Showed that the mapping G from SO3 matrices to another representation is important for learning. Namely, if such a mapping, called a section, is continuous, then this facilitates the learning of arbitrarily large rotation targets. Critically, our symmetric matrix representation admits a continuous and differentiable, or smooth, section, which we prove in Theorem 1 of our paper. To validate the hypothesis that continuity matters for learning, we trained a network to estimate the alignment between synthetic point clouds. Our findings indicate that our representation, shown here in blue, performs comparably to the continuous representation proposed by Giamou et al., and both significantly outperform the discontinuous unit quaternion formulation, especially when rotations with magnitudes close to 180 degrees are included in training and test data. Next, in what sense is our representation a belief? Well, consider the Bingham distribution, which can be used to define antipodally symmetric probability densities on the unit sphere in any dimension. Serendipitously, our symmetric matrix A defines a Bingham distribution over the three-dimensional unit quaternion sphere. This allows us to interpret our representation as encoding a belief over SO3. Further, we demonstrate through experiments on kitty data that we can threshold a dispersion coefficient based on the eigenvalue gaps of our learned matrix A to detect and reject out-of-training distribution samples at test time. We show the power of this approach by artificially corrupting test images with dark rectangular regions. This technique, which we call dispersion thresholding, requires no additional training or parameter tuning and outperforms an autoencoder-based novelty detection mechanism while maintaining high precision on all three kitty test sequences. In addition to the kitty dataset, we further evaluated our OOD detection scheme using data collected with a micro-aerial vehicle, flying between indoor and outdoor environments. We trained each model with outdoor data alone and found that our approach was able to compete with a separate autoencoder mechanism when exposed to indoor and transitional images at test time. In summary, we have created a simple and elegant representation for rotations that is smooth, probabilistic, and easy to implement. Our method incurs some additional computational cost, but this is marginal in many realistic scenarios. In future work, we're interested in further investigating the OOD mechanism we propose. Finally, we invite you to use our representation in your own work. You can clone our repo to get started. Thank you.